So we're going to start trying to graph these polynomials, which we've graphed quadratics and linear equations before, but we've not graphed higher degree polynomials, which is kind of the end goal of today. So we need to get some vocabulary straight. So there's going to be a lot of vocabulary today. The degree of a polynomial is simply the largest exponent in the polynomial. It's typically the first exponent in the polynomial, especially if it's written in the correct order in standard form, it will be the first one. Otherwise, you're looking for the largest exponent. What's called a leading coefficient is the coefficient or the big number in front of the variable with the largest exponent. So once you find the term with the largest exponent, the exponent is the degree, and the coefficient is called the leading coefficient. Cool, great, awesome. So if we look at the example right here, what is the biggest exponent in that? Exponent is the little number. 4. The largest exponent is 4. Yeah, the little numbers. Typically, it's the first term, especially if it's written in standard form, but you're looking for just the largest exponent, which means we look at that particular term, and the coefficient in front of it is called the leading coefficient. And leading coefficient has a lot of letters in it, so we're going to shorten that to LC. So if we were answering the questions below it, it would be degree 4, and its leading coefficient would be the number -6. Does that make sense? Degree and leading coefficient. Cool. Now the degree and the leading coefficient actually tell us a lot about that polynomial. Specifically, the degree tells us what type of polynomial it is. We've worked with the first 3 rows of this table before. If it has degree 0, meaning that this would be the largest exponent right here, the like straight up number by itself, it is called a constant function. An example is just like the number 5. If the first power, or just the x variable, is the largest exponent, it's called a linear equation, and it will look like this. If the biggest degree is 2, that's called a quadratic. Do these words look familiar? Cool. After that, we have a few more fun names for it. If you look at the next one, the largest exponent is 3. That means it's a degree 3. That's called a cubic function. Say that word, cubic. Like a cube, like when say 3 cubed, there's a 3 up there. A cubic function is a function with a degree of 3. Then if you look at the next one, it has a degree of 4. That's its largest exponent. That's called a quartic function. Say that, quartic. Say it, quartic. It's like a quarter. How many quarters are in a dollar? 4. That's why the 4th degree is called a quartic polynomial. And after that, mathematicians got lazy. We don't really use the names for anything after a quartic. You just start numbering them. So this one that has degree 5, we don't necessarily have to call it a quintic function, which would be its technical name. You just say it's 5th degree polynomial. The next one would be called a 6th degree polynomial and a 7th degree polynomial. So we kind of gave up on the namings after 4. So you have constant, then linear, quadratic, cubic, quartic, 5th, 6th, 7th, 8th. We gave up on the naming after that. I would love for you to memorize them. The first 3 should be easy. We know these, right? So then cube, you just think about cubing something. And quartic, just think about quarters. So yes, I want you to memorize them, but it should be pretty easy to file those away. Quarters, 4. Okay, now this end behavior, or these 2 things, the degree and the leading coefficient, help us out with something called end behavior. Now this is super important. This is kind of the main gist of today. This is what I really want you to be able to do. So put like an exclamation point next to this, a star or something. End behavior is the main goal of today's lesson. End behavior describes how a function behaves, or the direction it goes, as x approaches negative and positive infinity. It is based on the degree of the polynomial and the leading coefficient of that polynomial. So you only need to know its degree and the leading coefficient, and you're able to answer the end behavior question. End behavior itself is not confusing. The notation we use for end behavior is pretty advanced. So if we are looking at the left end behavior, meaning if we have a graph and we look at the left side of the graph, you're looking like over here, right? This is the left direction. You'll look at the left arrow of the graph and you write this following statement, like this whole thing is what you would write down right here. So highlight that. You would say, literally writing down A as for as x arrow. That arrow means approaches. So as x approaches negative infinity, f of x approaches either positive or negative infinity. The only thing that changes is whether you put positive infinity or negative infinity in the second part. For the right side, we write the following. What's the only difference you notice from the first thing I highlighted in black to the second thing I highlighted in black? Perfect. Left is the negative direction, which is why there's a negative here. So if we're talking about the right side, we're talking about positive infinity. But again, all you have to do is look at the arrows and decide if the graph is going up or going down, and that will change how you answer the question.
Are the arrows going to be going to the right too?
They should, the little arrows should always go to the right. This arrow, by the way, this is probably important to write down. When you see an arrow like that in math, it is the word approaches. So don't say arrow, say approaches. You would say as x approaches infinity, f of x approaches positive or negative infinity. That's how you'd say that. Now this is not going to make sense till we do a couple examples, and I promise you it's confusing until it's not confusing, so stick with me. Some hints for you that'll be very, very helpful. If the degree of the polynomial is even, so an even number, 2, 4, 6, 8, then the arrows are going to go the same direction. If the degree of the polynomial is odd, so an odd number, 1, 3, 5, 7, the arrows are going to go the opposite directions, which is very helpful. Odd, opposite, odd, opposite, odd, opposite. The leading coefficient tells us about the right side arrow always. If the leading coefficient is positive, that means that you're going to infinity. If the leading coefficient is negative, that means you're going to negative infinity. It's down, so negative infinity. Another note for yourself, the stuff we've highlighted in black, that is the correct way to write it. Your homework is going to flip-flop the way this and this are written. It's going to put the f of x first and the x approaches second. It's the same exact thing, just make sure the x and the f of x are exactly what you want. Okay, so this page just kind of has some definitions to get us started. If we go to the next page of our notes, we're going to actually start putting it together. There are only 4 options for end behavior, which means there's only 4 things we need to study on. End behavior is how a function behaves, like we said, as x approaches negative infinity and x approaches infinity. Right now, I want you to circle the one that says x approaches negative infinity, and I want you to write the word left next to it. I also want you to circle the one that says x approaches infinity, and I want you to write the word right. So when we're talking about negative infinity, we're talking about the left side for x, and we're talking about positive infinity for x, we're talking about the right side. It is all determined by the degree of the polynomial and the leading coefficient. Your only options are for the degree to be odd or even, and the leading coefficient to be positive or negative. If you have an odd degree polynomial, so odd degree polynomial, and your leading coefficient is some positive number, then odd means opposite. So my arrows for this graph will go opposite directions. So they should not be going the same direction. And because it's positive, the leading coefficient tells me about the right side. The right side arrow should be going up because the leading coefficient is positive. And since it's odd, the left side arrow should be going down because they have to go opposites. What this means for us is any polynomial we have that is an odd degree and positive, at the end we'll have arrows that do this. Don't write anything down for a hot second. Look at my board. It could look like this. Don't write anything down. That is an odd positive. It could look like this. that is an odd positive. It could look like this. I don't care what's happening in the middle. End behavior tells us about the end, not about the middle. It's not called middle behavior. It's called end behavior. So no matter what happens in the center, at the end, the arrows will be going up on the right and down on the left. Okay, now you can pick up your pencil and write it. So if we were to describe end behavior for an odd positive graph, we would say, and this is the blanks at the bottom, as x approaches negative infinity, that's the left side, f of x approaches negative infinity. Now, why did I put negative infinity for the left side? Look at the left of your graph. What's happening? It's going down. So we say negative infinity because the y values, or f of x, is going downwards, which means, what am I going to put on the next blank? Positive infinity, because on the right side, which is x approaching positive infinity, that arrow is going up. End behavior, that's it. We're just talking about what direction the end arrows are going for any particular graph. That's it. Now let's switch it up a little bit. This time, we still have an odd polynomial, so the degree is some odd number, but my leading coefficient is negative. What does that mean for my graph? It's going to be going down. So the leading coefficient controls the right side. My right side will be going down because the leading coefficient is negative. Odd polynomials have to go the opposite direction. So my left side should be going up, which means that on my graph, on the left side, I have an up arrow, and on the right side, I have a down arrow. And in between it, I don't really care what happens right now. We're talking about end behavior. It, again, could look like this, or like this, or like this. Either way, the end arrows will be going the direction we drew them. That looks crazy, so I'm going to just leave it as something simple. That was an ugly line. Let me try again. Okay, if we answer the actual end behavior question here, the way that we answer it, for the first line, we would say, as x approaches negative infinity, f of x approaches what? Positive, because negative infinity for the x means looking at the left side of your graph. My left arrow goes up. My right arrow goes where? Down. So the next blank would be negative infinity. Okay, cool. Those are my odd polynomials. Then I have my even polynomials. Even polynomials, we wrote on the other page that they're going to go the same direction. So if I know that the degree is some even number and the leading coefficient is positive, the leading coefficient controls the right arrow, and this right arrow says up. But if I need them to go the same direction, which direction does my left arrow go? Also up. Which means my end behavior for this graph is going to look something like this, where both arrows going the same direction because it's even, and that happens to be up. Now, what happens in the middle of them might look like this. What kind of graph is that called? Do we remember? Quadratic. It might do something different in the middle. It might do something like this. That's what a quartic function will look like. Or it might do something crazy like this. I don't care. We're not talking about middle behavior. We're talking about the end arrows. But I'll make it look nice to leave it on here. Okay. In which case, if we were answering the questions the way we write end behavior, we would say, as x approaches negative infinity, f of x approaches what? Positive infinity, because the left arrow is going up. As f of x approaches positive infinity, as x approaches positive infinity, f of x approaches also positive. They have to go the same direction. If it's even, they're both going to go the same direction. Notice that every single time I do this, the x approaches has to do one negative, one positive. The x approaches has to do a negative and a positive because we're talking about the left and the right. What do you think is going to change then if I have an even degreed polynomial but the leading coefficient is negative? They're both going to go down because the right side is controlled by leading coefficient, And the left side is controlled on whether it's even or odd. Since it's even, they go the same direction. Which means my end behavior for this will be down and down. Again, doesn't really matter what happens in the middle. That's not what we're talking about just quite yet. We're talking about end behavior. So if we answer the questions for end behavior, as x approaches negative infinity, f of x approaches negative infinity because it goes down. And as x approaches positive infinity, f of x approaches also negative infinity because the arrows are going down. So we're all only talking about what's happening on the left, what's happening on the right. The notation is weird, I get it, but it's just like, where's the arrows going on the left and the right? It is entirely controlled by the degree and the leading coefficient. So let's look at this for a second on the inside. Without graphing, we're going to describe the end behavior of these functions. Because like 1000%, you could type this into your calculator, look at a graph of it and be like, aha, the arrow is going up and then down or something like that. But it is easier than that because we don't even need to spend time typing it into a graph. What is the degree of question number 1? 4. Remember, degree is the largest exponent. 4 is my largest exponent. So my degree is 4. Is that an even or an odd number? Even. Okay, great. Now I just need to look at my leading coefficient, but that is the coefficient attached to that variable. What is the leading coefficient here? Negative 0.05. So again, that's a negative number. I don't care what negative number it is. It could be an ugly decimal like that, but it's a negative number. So in the little parentheses shortcut arrows, the right side, which is this part of the circle, is that arrow going to be going up or down?
Down.
Down, because my leading coefficient is negative. But it's even. So should the other arrow be going up or going down? Down, because even means they go the same direction. Cool, that's my shortcut. Now I just need to write it in the correct notation. And it's a mouthful, basically. You would write the full sentence out, starting with the left side. As x approaches negative infinity, f of x approaches negative infinity. This part right here means the left. This part right here means goes down. And based on what we said, the left side should go down, right? Okay, if we write the second statement, we would say as x approaches positive infinity, where does f of x approach? Negative infinity. Because we're saying here that the right side also goes down. So these two little math sentences, actually they're like a good little mix of English and math sentences, is how you answer the question. On your homework today, it's going to be drag and drop statements. And like I said earlier, your big ideas has flip-flopped the f of x and the as x approaches, but you can still match them up to how we've written these statements on your paper. I want to let you practice number 2 before we do number 3 together. So number 2 is for you. Identify first the degree and the leading coefficient and see if you can do it off your brain. If you need to flip back to the front page for the reference, you can, but give it a shot. What's the degree of this polynomial? 5. Which means, is that an odd or an even number? Odd. Okay, great. What's the leading coefficient then? 3, which again is a positive number. So we are following the rules for an odd positive polynomial. Positive is controlling the right side, so my right side is going up towards the positive numbers, and odd is opposite, so the other arrow should be going down. My sentences should be, as x approaches negative infinity, that's the left side, f of x approaches negative infinity, because that arrow went down. Did we get that part? Close? Okay. My second sentence is the right side. As x approaches infinity, f of x approaches infinity as well. And this is exactly what these little shortcut arrows are showing me. The left arrow went down. The right arrow went up. So I just translate that into the statements that we use. Yes? We're going to do number 3 together because there's a trick in number 3. It's not written in standard form. Did you notice that when you first look at it? So we can't just look at the first number and tell me the degree and the leading coefficient, or else that would be wrong. What is the actual degree here? 3, the largest exponent, not necessarily in front unless they follow directions and put it in standard form, which means that that is an odd, oops, wrong color, an odd polynomial. And what's the leading coefficient? -1. That's a negative number. So we're following the rules for odd negative. The negative part controls the right arrow. That means it's going down. Should the left arrow go up or down? Up, because it needs to be the opposite. Odd means opposite. Cool, we write our statements. I like starting with the left statement. It's not required that you do the left one first. In fact, some textbooks put the positive before the negative, but I don't like that. We would write as x approaches, and what do I put right there? Very good, negative infinity. F of x approaches, what do I put? Positive infinity, because the green arrow, which is my left side, is going up. If I switch to the right arrow, we would say as x approaches what? Positive infinity. F of x approaches negative infinity, because the arrow is going down. But I'm sure you're like, but Miss Quigley, what are we even talking about here? What I want you to do right now is in your calculator, I want you to type in this equation. So when you type an equation into your calculator, because we're going to get used to calculators other than Desmos since our SATs are coming up this semester for my juniors. March 1st, by the way, is when your SAT is. It's the free one you take at school. You're going to press the y equals button because f of x is the same thing as saying y equals. And you're just going to type in exactly what you have there. So 3x squared minus x cubed plus 9. I'll give you a second to type that in. I want you to practice. So since we've seen it in our calculator, as a note for yourself, I want you to sketch it real fast. We had a graph that just looked like this. Like, it doesn't have to be pretty. But didn't we have it where the left arrow went up and the right arrow went down? We have verified it on our graph. But typing all of that in takes a hot second. So if you're just wanting to figure out your end behavior, just look at your degree and leading coefficient, because then you don't have to beep, 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 type stuff in. Okay, cool. But speaking of graphs, because graphs are really the end goal of this, being able to graph polynomials or look at graphs of polynomials quickly, we're going to combine the use of the calculator with end behavior to sketch these functions a little quicker. So we're going to determine the end behavior and draw arrows, and then use our calculator to plot good points so we can sketch the graph. So if we look at the first, number 4 right here, what's the degree of that polynomial? 3. What's the leading coefficient? Great. So we know that this is degree 3, which is odd, and the leading coefficient is -1, which obviously is a negative number. For odd negative, what little arrows should I draw in those little parentheses? What should it be? Down on which one? The right side should go down, because leading coefficient controls the right. And what should happen on the left? Up, because it's opposite. Great. That means when I graph this function, no matter what happens in between, I know that at the end I will have an arrow going up on this side and an arrow going down on that side. Great. That's end behavior. I just need to figure out basically middle behavior. That's not a thing, but that's what I like calling it. Because this is end behavior. Now we need to figure out the middle. But what we're going to do is we're going to go to our calculator again. We're going to press y equals, and we're going to type in the entire equation. However, we're not pressing graph this time. You're going to press table. Table is a blue word above the word graph. So to get to the, whoa, what word did I just write there? Grabble. I combined the word graph and table. To get there, you'll press second graph to go to table. So I'll do this one along with you, but I'll have to show you on the not quite TI calculator. It works the exact same. once we have the values, we will literally just do this. I'm going to copy the table down onto my paper. I'm going to have -2 partnered with 3. -1 is partnered with -4. 0 is partnered with -3. 1 is partnered with 0. And 2 is partnered with -1. Those are all coordinate points that I can plot on this graph to make a very good sketch for the middle. I picked specifically from -2 to 2 because that's the middle of the graph, closest to the origin. So if we plot those points, it'll be -2, 3, -1, -4, 0, -3, 1, 0, and 2, -1. Polynomials require advanced connect the dots skills. When we did linear and quadratics, it was very easy to play connect the dots, but these don't really look like they go in a particular order, so you have to be very careful when you do the connect the dots step. To connect the dots, you start at the left end behavior, so you would put your pencil here on the left end behavior. You're going to go to the first coordinate point you can find. Then you're going to go all the way to the next one, even if it's far away. This is the next one. And then this one. And then this one. And then this one. And then you connect it with your other end behavior. It's advanced connect the dots. Start at the end behavior, hit all the important points, finish at the other end behavior. So if you didn't draw your arrows for end behavior when I did earlier, make sure that you have always drawn these arrows on your graph so you know that that's where you're starting and ending. The arrows take care of the end, the chart takes care of the middle. Shall we do another one together? I don't feel like we're ready for one on our own. Okay. Number 5. If f of x is equal to x to the 4th minus x cubed minus 4x squared plus 4, what's the degree? 4. That means it's an even number. What's the leading coefficient? 1. The invisible 1 right in front of it. Fabulous, which is a positive number. For even positive, which directions should the arrows be going? Both up. Very good, because even means they both go the same direction. Up means up. Cool, so I have my end behavior arrows that I can already draw for this graph. We'll go ahead and draw them in because that's our starting and our ending point for this graph. We just need the points in between, and we're going to utilize the calculator to do that. I'm going to show you one more time on the screen how to do that. So our middle terms based on our calculator for x and y are -2 partnered with 12, -1 partnered with 2, 0 partnered with 4, 1 with 0, and 2 with -4. Those are all coordinate points I can plot, and then I can play connect the dots. Now, -2, 12, is that going to make it on this graph? No, so I'm actually going to skip that one. I'll go to -1, 2, which is here, 0, 4, 1, 0, 2, -4. All right, advanced connect the dots here. We start at the left end behavior arrow. So put your pencil on the left end behavior arrow, and you're just going to go to the first coordinate point you run into. Boom. The next coordinate point I run into, is it up or down? Up. So I'm going to go get that one that's up. And then where do I go? Down. And then down again. And then I have no more coordinate points left, so what do I have to connect it to? The arrow back up at the top. Advanced connect the dots. But this is what the sketch would look like if we didn't press table and we pressed graph when we had it in our calculator. It would look something like this. Beep, 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 beep. Off screen. But end behavior makes that way easy to do without the use of technology. Like if you don't have a graphing tool, you just get all of the coordinate points. Now getting all the coordinate points, we did use a tool for that. But if you happen to not have a calculator that generates tables, here's how you would eventually figure that out. It would be by evaluating the function for different values. If you see this word evaluate, 99% of the time, it's asking you to plug in a number or compute a number. So for part A, what number is it telling me to plug in to the equation? 2. Yeah, don't overthink it. Which means anywhere there was an x a second ago, I'm going to place a 2. Just literally taking the x's out and replacing it with a 2. Notice that when I do this, what am I putting around all of the 2's? Please do that. You have to have the parentheses or else it will probably mess up. But once you do that, since I have no more variables left at all, I just go to the regular home screen of my calculator, like the one where you type stuff in, like plus and minus stuff, and you're going to type all of that in, meaning it will look something like this. I'll show you on the calculator. Pretty simple, right? Let's just make sure you got it. Part B is for you. What number are you plugging in part B? 0. Go ahead and do that. I want you to write it down on your paper first, showing me what you're going to type into your calculator, and then type it all the way in. So again, all we're doing is taking all of the x's and replacing them with zeros, using a ton of parentheses, and when you type it in your calculator, you should get an evaluated number, -3. Now, one thing I want to draw to your attention, and the reason we're having you do this last little part that feels like different than everything we did all day, did you notice that the problem in number 6 is the exact same equation as the one in number 4? I wouldn't have noticed that first, but did you notice that? So on number 4, when we answered these questions, we are able to use our calculator to make this table. But let's say perhaps you don't have a calculator that does tables. You can do this because what was partnered with 2 in our table? And what happened when we plugged in 2? What did we get? And what was partnered with 0 in our table? And what did we get when we plugged in 0? That's exactly what that table is doing. It's just doing it faster for you to save you time. So if you don't have a calculator that generates tables, you can evaluate all of the functions and get these beep, beep, beep coordinate points to play connect the dots with. So it's still doable even with old school technology.